Hello everyone. Today we'll go over some practice problems regarding simple harmonic motion. Starting off, a mass of half a kilogram is attached to a spring with an oscillation period of 2 seconds. What is the spring constant? So let's first write down our variables. We have that the mass is equal to zero point 0.5 kilograms. The period is equal to 2 seconds. Now we need to find the spring constant. We know that the formula for the period is equal to 2 pi multiplied by the square root of the mass divided by the spring constant. So we need to rearrange this formula to solve the spring constant K. Let's start by squaring both sides to get rid of the square root. So we have that the period squared is equal to 4 pi squared multiplied by the mass divided by the spring constant. Now from here, we can multiply the spring constant to this side and divide this side by the mass to isolate the spring constant. This gives us that the spring constant is equal to 4 pi squared times by the mass divided by the period squared. So plug in our values, we get 4 pi squared multiplied by 0 0.5 kilograms divided by 2 seconds squared. This gives us our value for the spring constant of 4.93 Newton meters. Next up, a simple pendulum has a length of 2 meters. Calculate its period and frequency. So this should be a fairly simple example. The period of a pendulum is given by 2 pi multiplied by the square root of its length divided by the acceleration due to gravity. Meanwhile, the frequency is the inverse of the period. So we can just solve the period first and then take the inverse to get the frequency. So writing out the values we've been given, we know that the length is equal to 2 meters and the acceleration due to gravity on Earth is equal to 9.81 meters a second squared. So plug in our values into the formula for the period. You get that the period is equal to 2 pi multiplied by the square root of 2 meters divided by 9.81 meters a second squared. This gives us the answer that the period is equal to 2.84 seconds. Now to find the frequency, I'll just write it down again that the frequency is equal to the inverse of the period. So in this case, we get that the frequency is equal to 1 divided by 2.84 seconds. Since 1 hertz is equal to 1 divided by a second, we get the answer that the frequency is equal to 0.35 hertz. For this next question, what is the period and frequency of a 50 centimeter long pendulum on the surface of the moon? The moon has a mass of 7.34 times 10 to the 22 kilograms and a radius of 1.74 times 10 to the 6 meters. So in order to do this, we need to first calculate the acceleration due to gravity on the moon. If you recall from dynamics, the acceleration due to gravity for a small object near a large object is equal to the gravitational constant, this capital G, multiplied by the mass of the large object divided by the distance between them squared. Since we're on the surface of the moon, it means that we'll just use the radius of the moon as the distance between the objects. Plugging in the values for this formula, we get that the gravitational constant times the mass divided by the radius of the moon gives us the acceleration due to gravity on the moon. Which is equal to about 1.62 meters per second squared. Now that we know the acceleration due to gravity on the moon, we can use the formula to find the period of the pendulum, which is equal to 2 pi times it by the square root of the length of the pendulum divided by the acceleration due to gravity. Now, let's write down what we know about the pendulum. We know that the length is 50 centimeters. So we need to put this into SI units, knowing that 100 centimeters equals 1 meter. This means that the length is equal to 0.5 meters. Now finally, we can put this value in the formula to solve for the period. So we get that the period is equal to 2 pi multiplied by the square root of half a meter divided by 1.62 meters per second squared. This is equal to 3.49 seconds. Now let's find the frequency. We know that the frequency is equal to the inverse of the period. So we just need to simply take the inverse of the period. This means that the frequency is equal to 1 divided by 3.49 seconds. This gives us our frequency of 0.29 hertz. For this last example, a 100 Newton force stretches a spring by half a meter with a 1 kilogram mass attached to it. What is the frequency of the oscillator? Let's start by writing down our variables. We know that the force is equal to 100 newtons. The displacement from its equilibrium position is equal to half a meter. And it has a mass of 1 kilogram. Now, to find the frequency, we can use the formula that the frequency is just the inverse of the period. Now, to find the period, we can use the formula that the period is equal to 2 pi multiplied by the square root of the mass divided by the spring constant k. So, rearranging to solve for frequency, this gives us that the frequency is equal to 1 divided by 2 pi, all multiplied by the square root of the spring constant k, divided by the mass. However, we don't have the spring constant k, so we need to use Hooke's law in order to find it. Hooke's law says that the force will be equal to the spring constant k multiplied by its displacement from its equilibrium position, x. So in order to solve for k, we need to take the force divided by its displacement and plugging in the values that we have. This is equal to 100 newtons divided by half a meter, which is equal to 200 Newton meters. Now we can use our formula for the frequency to solve for the frequency since we have all of the variables we need. Plugging in the values, we got that the frequency is equal to 1 divided by 2 pi, all multiplied by the square root of 200 Newton meters divided by 1 kilogram. This gives us our answer that the frequency of the oscillator is equal to 2.25 hertz.